And just to reiterate, one of the things we saw here, one thing that should have made this rotational section easier is seeing the analogies with translational motion. We saw how rotational kinematics is very similar to translational kinematics. So now that I think about that, maybe we should talk about one or two more things before we get on to torque. Remind me again what the rotational analog for this symbol is?
Delta theta.
Yeah, what's the name of this?
Angular displacement.
Yeah, this is displacement, and this is angular displacement, or maybe rotational displacement. What would be the an analog here?
Omega.
And this stands for?
Angular velocity.
Yeah, this is velocity, or linear velocity. This is angular velocity. And this symbol would be?
Alpha.
And that stands for?
Angular acceleration.
Good. Now, one thing I didn't talk about yet that I should have is, so the last problem that we did, we were able to solve it purely by using rotational concepts. We didn't have to use any translational concepts. In fact, when you tried to use a translational concept, it just messed us up when we were thinking about the centripetal acceleration. However, on a more difficult problem, you have to use both translational and rotational concepts, and you have to move back and forth between them. So it would be nice if we could figure out the rotational idea from the linear idea, or figure out the linear from the rotational. Well, here's the relationship between displacement and theta. Although, for this equation, instead of calling this displacement, I think I'll just call it distance. This basically tells us the translational distance that a point on the wheel has moved, for example. So if a point on a wheel is moving and you want to know what distance it's moved in meters, well, if you know theta, you can work this out. This equation doesn't come up too much, but this next equation comes up a lot. If you know the angular velocity, you can figure out the linear velocity using an exactly analogous equation. So what would be the analogous equation for v to the one we used for d? What do we need to multiply omega by to find v? Well, by analogy, we'll just multiply it by r again.
Okay.
I probably should have said what r is, shouldn't I? Well, r is the distance between the point and the axis of rotation. R is the distance between the point you're focusing on and the axis of rotation. For example, if we have a wheel that's rotating around its center, R would be this distance. Or let's say you have a rod that's rotating around this point, like this. Well then, this would be R. Because this is the distance, at least this is R if we're focusing on this point. Okay. If I was focusing on this point, then this would be R. So the same object can have a bunch of different R's depending on what point you're focusing on the object. I should have specified that as well. One thing that's confusing is that we kind of use R for two different things in physics. We use it for distance and radius. A distance and a radius. That's a little confusing, but actually, again, there's a reason that physicists use the same variable for both of those. So in a sense here, R is a distance. It's the distance between the axis of rotation and the point you're focusing on. However, there's also a sense in which it's a radius, because you can see here, you can always draw a circle that's traced out by the point that's rotating, and then R would be the radius of that circle. So you can see why we're using a symbol that also means radius to really stand for distance. But it still is probably going to confuse us if we think of this as radius. It's better to think of it as distance. The distance between the axis of rotation and the point we're rotating around. Well, that brings up a point that's going to be very important from now on. In order to solve rotation problems, you need to identify the axis of rotation. You actually have to identify and draw the axis of rotation. Sometimes that's called the pivot point. For our purposes, the pivot point and the axis of rotation will be the same thing. For example, in this problem, here's the axis of rotation. Now, oftentimes you can't really draw the whole axis of rotation because it's perpendicular to the page. For example, here, the axis of rotation is parallel to my chalk holder. It's going into the board at this point here. This is the line that this is rotating around. All we can do is draw the point that we're pivoting around, but that's one point on the axis of rotation. So you draw the axis of rotation, or if it's perpendicular to the page, you draw the point where the axis of rotation hits the page. Here again, here's the axis of rotation parallel to my chalk holder, and this point indicates the axis of rotation. So anytime we have an equation that deals with r, we can't figure out what r is without locating the axis of rotation and locating the point we're focusing on, and then seeing the distance between them. So now this is a very important equation that tells you how to find the linear velocity if you know the angular velocity. Now these equations I'm putting on the board now only work when you use radians. You cannot use revolutions. Even if other things are consistent, this has to be in radians. I said a second ago that the kinematics equations, you don't have to use radians as long as you're consistent. But that's not true here. We must use radians for these. Let's stick with revolutions per minute for a second. Let's say that we have like a disk that's rotating, some kind of turntable that's rotating. So this is a solid object that's rotating. Well, let's say that this point is rotating at 3 revolutions per minute. That would be its omega. What would omega be for this point? How many revolutions does this point make in a minute? If you actually form a mental picture of this rotating, we should be able to see how many revolutions this point makes in a minute if this makes 3 revolutions in a minute. And this is a solid object again that's rotating around the center.
1.5.
So in 1 minute, this point has gone through 3 rotations. But notice that wherever this point is dragged along, isn't it? Mm-hmm. So after this point has made 1 rotation, this point must also have made 1 rotation. Maybe it would help to think about this, say, like, what do you call a merry-go-round? Let's say this is a solid merry-go-round. And let's say that there's 1 person here and 1 person here.
Okay.
Well, if this person goes around 3 times per minute, how many times will this person go around?
3 times.
Because it's a solid object. They're all going around at the same point. So this is something that's very handy about rotational velocity. It's the same for every point on a rotating object. The rotational velocity is the same for every point on a rotating object because the object is rotating as a unit. Maybe that merry-go-round analogy makes it easiest to see that. As you go around, you're not going to leave this guy behind you. He's going to be keeping pace if the merry-go-round is solid. All right, in order to use this equation, though, we have to put things into radians. Well, what would this be? How would we put this into radians? How many radians would this be per minute? You can work that on a paper if you need to. And I guess we shouldn't use a calculator. Let's keep talking about this in terms of pi.
Oh, okay. 6 pi.
Yeah, in fact, maybe you don't even have to write this down. We know that 1 revolution would be 2 pi. So 3 revolutions would be 6 pi. 3 revolutions is 3 circles or 6 pi. So we're going through 6 pi revolutions per minute. Now this is still omega. It's just omega in different units.